There are dozens of performance metrics being used in hydrology, but each one captures something different: peaks, timing, volume, and low flows. But here's the problem. Relying on a single metric or using the wrong one can make your model evaluation misleading. The reality is this: hydrological modeling performance is inherently multi-dimensional, so the performance metrics should be selected wisely to capture all required aspects of model adequacy. In this video, we explore why using a single performance metric fails. Then we introduce commonly used objective functions and demonstrate through numerical examples how multi-objective evaluation leads to a more robust assessment. Stay with me. Hydrological models are evaluated by comparing simulated discharge against observed discharge. The fundamental question is straightforward: how well does the model reproduce observed behavior? However, performance is not a single attribute. Hydrological model performance is inherently multidimensional due to the following 4 reasons. First, flow regime diversity, such as high flows, medium flows, low flows, and recession characteristics. Each regime reflects different hydrological processes and model behaviors. Second is temporal dynamics, represented by peak timing, event duration, and flow sequencing. A model may reproduce magnitudes well but misalign timing, which is critical in many applications. Third is error characteristics, for example, systematic bias versus random error, or persistent underestimation versus sporadic deviations. Different metrics respond differently to these error structures. The fourth one is application-specific requirements. Model adequacy is context-dependent. For example, in flood forecasting and warning systems, the critical parameters are generally peak flow, time to peak, and rising limb characteristic, while low flows and long-term volume are not that critical. Or in another example, for water supply planning, critical parameters are low flows, total yield, and base flow recession, while peak flows are generally not that critical. These 4 highlight a key limitation. No single scalar metric can comprehensively evaluate model performance. Therefore, multi-objective evaluation is essential. Now let's go through the commonly used objective functions in hydrological modeling. First, Nash-Sutcliffe efficiency, or NSE. It is the most widely reported metric in hydrological literature. It is good for general model performance assessment and model structures or parameter sets comparison. Limitations are as follows. First, oversensitive to peak flows. Second, insensitive to low flows. Third, insensitive to systematic bias. It can still score well despite consistent over or under prediction. Fourth, insensitive to timing errors. Early or late peaks with the same magnitude don't reduce NSE much. Fifth, scale dependent. We can't compare NSE across catchments with different flow magnitudes. And finally, NSE can't distinguish between different types of errors. The second one is log-transformed NSE. It equalizes the importance of flows by reducing the data range through log transformation. It can complement NSE by revealing model deficiencies in low flow predictions and base flow evaluation. Limitations are as follows. First, it can't handle zero flows. Therefore, we need to replace zeros with constant values or exclude them. However, the arbitrary constant can affect the results. Second, less interpretable than NSE, as the log space is not intuitive. Third, Kling Gupta efficiency, or KGE. It uses 3 components. Correlation R, which measures linear relationship indicating timing and shape matching. Variability ratio, or alpha, which measures whether simulated flow variability matches the observed one. And finally, bias ratio, beta, which measures systematic over or under prediction. KGE is suitable for comprehensive performance assessment, diagnosing specific model deficiencies through components, and comparing performance across different flow regimes. KGE is generally better than NSE for ungauged catchment applications, as it is less affected by mean flow magnitude. Limitations are as follows. First, it is less popular than NSE. Second, components can partially compensate. Third, it still doesn't address timing errors explicitly. And finally, equal weighting of components R, alpha, and beta may not suit all applications. Next is coefficient of determination, or R-square. It evaluates the strength of the linear relationship to determine whether the observed and simulated flows track together. It is good for quick screening of model adequacy. Limitations are as follows. First, insensitive to bias. A model that systematically doubles all flows can give an R-square of 1. Second, insensitive to scale. Third, it only measures correlation. Fourth, it is often misinterpreted. A high R-square doesn't mean good predictions. And finally, the linear assumption, as it may miss nonlinear relationships. Next is root mean square error, or RMSE. It provides an intuitive interpretation of model performance in terms of an average error magnitude. Similar to NSE, it penalizes large errors more than small ones. It is good for comparing models on the same catchment and engineering applications requiring error quantification in physical units. Limitations are as follows. First, it is scale dependent. Second, being sensitive to outliers. Third, no context. An RMSE of 10 cubic meter per second could be good or bad depending on flow magnitude. Fourth, it doesn't indicate error direction. Also note that RMSE has a normalized variant known as NRMSE. It allows cross-catchment comparison, often expressed as a percentage. Next is mean absolute error, or MAE. It gives an average error magnitude without amplifying outliers. It is a more robust alternative to RMSE when outliers are present. This is good for simple interpretability and when outliers shouldn't dominate. Limitations are as follows. First, being scale dependent like RMSE. Second, it doesn't indicate error direction, whether they are positive or negative. Note that comparing MAE and RMSE can give more insights. Generally, RMSE is equal to or larger than MAE. If RMSE is much larger than MAE, it indicates that large outliers dominate the error. If RMSE is approximately similar to MAE, it suggests that errors are relatively uniform. Next is percent bias, or PBIAS. It focuses on total volume and offers a simple interpretation of volume error. It can reveal systematic bias invisible to NSE or R-square. PBIAS is suitable for water balance assessment, detecting systematic bias, long-term yield estimation, and water resources planning. Limitations are as follows. First, it ignores timing completely. Second, it can be misleading, as an overpredicted flood or underestimated base flow can still give near-perfect PBIAS. Third, it doesn't assess error distribution and just gives a total volume difference. Next one is volume error, or VE. Same as PBIAS, it is well suited for water balance verification and long-term runoff assessment. Note that VE and PBIAS have opposite signs. Next is peak flow bias, also known as peak error. It focuses on model performance in peak estimation. It is essential for flood forecasting and warning systems, infrastructure design, and emergency management. Although peak accuracy is necessary, it is not sufficient if used alone, so always combine with other metrics. Note that PFB is sensitive to definition when having multiple peaks. And last one is time to peak error, or TPE. It is essential for flood forecasting and warning systems and emergency management. Now let's go through a few numerical examples. Our first example is a double peak hydrograph. As you can see, the NSE and Log-NSE values are both above 0.9, which are considered as good, but of course Log-NSE is slightly lower. When we go to R-square, we have a near perfect value of 0.998, and then when we move to KGE, we can see that the performance is slightly lower than NSE. Looking into the three components of that, R, alpha, and beta, we can see that the systematic overestimation of the simulated hydrograph is captured by alpha and beta. That's the reason that KGE is slightly lower. That's why KGE is considered as a more reliable metrics compared to NSE. Now let's move to RMSE and MAE. We have got quite similar values. That's an indication of a uniform distribution of errors over the hydrograph. Then we move to PBIAS and VE for volume assessment. They are calculating the same thing but with opposite signs. So a positive VE and a negative PBIAS means overestimation. The value is 17.45%. That is falling in the satisfactory category. So it's not that good, but still satisfactory. And when it comes to the peak flow bias, the value is 9.1%, relatively good. And we don't have any timing error. So the timing is perfect in this hydrograph. Overall, we can consider this simulated hydrograph as a good one because overall shape of the hydrograph, the volumes, and also the peak and timing have been simulated quite well. The second example is a shifted or delayed hydrograph. So if we look at NSE and Log-NSE, the values are quite close to each other. The KGE is slightly better, but if we look at the components, we can see that the correlation is the one that is relatively lower compared to the alpha and beta. and that's because of the shifting effect that we see here. R square is also 0.73, which is an indication of a relatively lower correlation between observed and simulated values. The RMSE and MAE values are quite different, and that's an indication of a non-uniform distribution of errors. The PBIAS and VE are fantastic. They are less than 1%. When it comes to PFB, we have a very good performance. The peaks are exactly similar in the simulated and observed, but unfortunately shifted. So the TPE value here is 2 days delay, which is generally not acceptable for flood forecasting or warning systems. Overall, the hydrograph has a systematic issue, and a good performance in peak or volume should not deceive us. Our third example is the case that our simulated hydrograph is double of the observed value. So it's a systematic error again. So if we look at the parameters, NSE and KGE has given negative values, an indication of a very poor performance. If we look at the Log-NSE, it is also not that good because we have overestimation in the low flows as well. And interestingly, R square gives a perfect value of 1, which could be deceiving if we just rely on R square as our only performance metric. If we look at the RMSE and MAE values, they are slightly different, an indication of a non-uniform distribution of errors over the hydrograph. And when we come to PBIAS and VE, we have 100% overestimation. And then when we go to the PFB, same, we get 100%, means that the simulated peak is double size of the observed one. And of course, TP will be 0 because the timing is perfect in this hydrograph. Overall, this hydrograph has systematic issue, and relying on a single parameter like R square could be deceiving. If you are interested in seeing a detailed calculation of these metrics, please watch our extended example in the second episode of this video. Given the inherent limitations of objective functions, model evaluation should follow a structured approach. First, define application requirements. Identify critical flow components, establish acceptable error thresholds, and consider relevant regulatory or design criteria. Second, select appropriate objective functions. Use multiple metrics aligned with application goals. Include diagnostic metrics such as KGE components, and adopt recommended multimetric suites where available. Third, apply multi-objective calibration. Recognize that simultaneous optimization of all metrics is not feasible. Use weighted objectives or Pareto-based approaches. And finally, accept trade-offs based on application priorities. Lastly, report transparently. Specify the intended application context, report all relevant performance metrics, not just the best one, document calibration objectives and their weights, and clearly communicate trade-offs and limitations. Ultimately, hydrological modeling is not about optimizing a single performance metric. It's about developing models that are fit for purpose, transparent in their limitations, and robust under uncertainty. If you found this video helpful, please share it with others and subscribe to the channel for more videos like this. Thank you for watching, and I look forward to seeing you in the next one.